So good morning, everyone. I'm from Sri Lanka, so it's still morning, 7 a.m., but good afternoon for everyone else. Today I'm going to talk about technical anomalies in water quality data from in-situ sensors. In this talk, what I'm going to do is I'm going to answer three main questions, and that lay the foundation for our upcoming talk on the framework for detecting anomalies in water quality data. So this is our team. This is our team, anomaly detection team. The work that I'm going to present today is a joint work of our anomaly detection team, consists with multiple brain areas. Okay, with that, I'm coming to our first question: what is an anomaly? So this is a really important question because the anomaly detection problems, the anomaly detection techniques can be highly influenced by the way we define an anomaly. So when it comes to, I'm a statistician by training, so when it comes to statistics, this is how we normally define an anomaly. A statistical anomaly is an observation that deviates markedly from other members of the dataset. So this is one general common definition that we use to define an anomaly. With that, I'm coming to the water quality problem. So now, as Ryan mentioned, when it comes to our water quality problem, there are two types of anomalies. One is water quality breaches associated with real events, and the other type is technical issues in sensor equipment. Now, as Kat mentioned, in this work, our focus is mainly on this type of anomalies, the technical issues in the sensor equipment. Okay, with that, I'm coming to this real-world data set. Now, you're already familiar with this data set. Kat introduced you to this data set during her talk. So basically, now this is a turbidity series, and here the black color dots represent technical anomalies in this series, and the gray color points represent typical point. Now, when it comes to as a statistician, if I just apply my statistical knowledge, now I will call these as statistical anomalies, because according to our definition, now these points are somewhat far away from the typical behavior. But according to water quality experts, this is not an anomaly, it's a real event. Now they want us to identify, they want us to come up with an algorithm that claim these as typical points instead of anomalies. Now let's think about these type of technical issues. Now, according to our definition, this is not a statistical anomaly, but according to water quality experts, these are technical issues. Now we need to know, our challenge is we need to come up with an algorithm that can detect these as anomalies and ignore these being detected as anomalies. So now this is kind of the main motivation of our proposed algorithm. Now our challenge was to identify these technical issues from these real events and other typical points. Okay, so for this, we use, I'm going to explain our algorithm using a case study. So for this case study, we used Pringle Creek data from a National Ecological Observatory Network aquatic site located in Texas. One reason for us to use this data set is because NEOM usually has two sensor locations on any river in the network where water quality is measured using in-situ sensors. And during this process, we are very grateful to Guy Litt. He helped us a lot in understanding the nature of the data coming from this website. Okay, so with that, I'm coming to the definition now that I'm coming to our proposed algorithm. In our proposed algorithm, this is how we define an anomaly. In this work, we define an anomaly as an observation that has unexpectedly low conditional probability density. I know that sounds a bit theoretical, but don't worry about that. I'm going to talk about it in detail in our upcoming slides. So when it comes to this definition, the key word that I want to highlight is this phrase, the low conditional probability density. Now, what do you mean by low conditional probability density? What do you mean by conditioning on something? For this, let me use a little analogy that might help you in understanding this. So imagine your sensor is a person standing on a bridge. And all of a sudden, he sees river ducks floating down the river. So in such situation, so it's something unusual, something unexpected. So we call it as an anomaly. Now imagine a second situation where you got a friend 200 meters up the river standing on another bridge. And now 2 hours ago, he yelled out to you saying, ducks are coming down the river. Now, at this point, I'm expecting to see the river ducks. So now when they appear, that's not unusual because previously I got information from my upstream friend, from the friend who is at the upstream. Now it is not, since we have previously got this information, we are expecting this to happen, so we don't call it as an anomaly. So this is, so if I put all these ideas together, so basically now here we have downstream sensor, we have upstream sensor. When we call, what we call conditioning is incorporating new information coming from different sources. Okay, with that, now, you know, conditioning is basically the new information coming from different sources. Now, if you think about new information, we can think about different types of conditioning or different types of new information. So let me first start with one site where we have only one site. Now, in that case, we have only one site and we have sensor. And let's imagine that we want, let's think about this as a downstream turbidity series. And let's imagine we want to identify anomalies in this downstream turbidity series. Now, one conditioning type that we can think is, we can think about the information coming from downstream past observations. So using that new information, I can talk about, I have my past observation. Using that past observation, I can talk about the current status of the current observation. So that is one conditioning type that we can think. Another conditioning type that we can think is contemporaneous downstream observations. Here, contemporaneous downstream observations means now I want to identify the anomalies in my downstream turbidity. I'm going to use the information coming from other variables of the same time. So contemporaneous variables, contemporaneous downstream observations means the other variables of the same time. And now using the information, new information coming from other variables, I can think about the behavior, I can predict the behavior of the downstream turbidity, and through that I can identify the anomalies. So this is basically, this type 2 conditionings we can think when we have only one sensor. So this is what we actually did in our previously proposed algorithm, oddwater. Kat gave a small introduction to our previously proposed algorithm. There, our focus was only on one site, and in that site we want to identify the anomalies. For that we use both lag downstream observations and also contemporaneous downstream observations. Now, oddwater framework we have published in 2 papers, and in addition to that, our proposed framework is implemented in an R package called oddwater. And if you are interested in that, you can find the development version of our oddwater package in my GitHub account. Okay, so that is basically the new information that you can go and get from the same site. Now, in this work that we are going to propose, the new algorithm that we are going to propose, we introduce another additional conditioning. So basically, we try to incorporate the new information coming from another site. So in our proposed algorithm, the conditioning coming, the new information that we get that information by considering 2 sensors in close proximity with connected flow. For example, imagine now the blue sensor, that's where I want to detect anomalies. So that is my downstream turbidity. And now I'm going to take the information coming from the upstream turbidity to talk about the behavior of my downstream. And thereby, I'm trying to identify the anomalies in my downstream turbidity. So conditioning on the upstream variables. And the one thing that we notice is when we study these Finger Creek data, one thing that we notice is Finger Creek experience high flow in spring when rainfall is heaviest and low flow during typical dry summer. So basically, they have different lag times. They have different lag times between those two information. Basically, lag time means the time it takes to get the upstream information to the downstream information. Depending on the weather condition, it will take different times to pass this upstream information to downstream information. And now, so in this proposed framework, our first challenge was to identify that lag time, the time it takes to pass the upstream information to downstream information. For this, we proposed a new algorithm, a new methodology called conditional cross-correlation. So I will talk more about that one. So basically, under using conditional cross-correlation, first we identified the lag time between the downstream turbidity and upstream turbidity, and then after that we use that information to predict the downstream turbidity. So for example, let me elaborate it a little bit further. For example, imagine now you have two sensors. Now, two streams. So this green color one is the upstream turbidity, and the blue color one is the downstream turbidity. Now, I want to identify these outliers available in my downstream turbidity. Here we have sudden spikes. Those are high priority anomalies. And here we have a drift. This is a low priority anomaly, but it's a very important and challenging type. And here we have high variability. Now, how are we going to capture these information? So to that, we use the information coming from upstream turbidity. What we do is, using the information, using this upstream variable, we predict the downstream behavior. So for example, you are done this purple color one now will be the predicted values that you get by using the information coming from upstream. And then after that, we think about the difference between the predicted values and the actual observations of our upstream variable. And now you can see, now since we don't have these technical outliers, now if it is a technical outlier, you will experience that they do not share technical outliers between variables. They share only the water quality events between the two sensors. So if there's a technical outlier, now since I cannot see that in my upstream variable, it will not predict that behavior in my downstream. So now when I think about the difference between my predicted value and the observed value, I can see a big deviation. Now using that information, we can clearly identify these anomalies. So now in this one, again, another thing that I want to highlight is, now here we have a small condition now, and now we are using upstream behavior to predict downstream behavior. So we assume that our upstream variables is free from outliers, because then we can get a good prediction for our downstream variables. And then after that, we combine all these conditioning, this new information to differentiate technical issues from real events. Now through that, you can also see that here, this is, as a statistician, we will call it as an outlier, but it is a real event. Since it is a real event, we experience the same thing in our downstream variables. So now since it predicts that one, we cannot really see a big difference between the observed values and the predicted values. And that prevent us claiming this actual event as an anomaly. So that is another advantage that we get by taking two sensors that are close to one another. Basically, by combining all these three information, it advances the outlier detection capabilities of our algorithms. And also, in addition to that, it also focuses on both high priority and low priority anomalies. Okay, so now I was talking about three conditioning types. So the first two are based on the information coming from the same site, and the third information is the information coming from the last the other stream. Now my question is, why is it important to use various types of conditioning? Why can't we just rely on our last conditioning type? When we observe our finger tree data, we realize that during summer, so during summer there's a discontinuity between these two sites. During summer, surface flow tends to cease, creating disconnected pools of surface flow water along the channels. So in such situations, you will not be able to see a connection, a communication between your upstream and the downstream. Now, in such situations, we cannot use our third conditioning. Then we have to rely on our previously proposed algorithms that are based on the first two conditioning types. So having all these things together will actually improve the capability, the maximum capability, will allow us to get the maximum performance. Okay, so now how are the two approaches, oddwater and conduit-based approach, different? Basically, oddwater is the one, the feature-based approach that can talk about previously. We have already published that one. And conduit-based approach is the one that we are proposing right now. So what is the difference between these two? Why we need these two different algorithms? Okay, on the left-hand side, I'm talking about our previous algorithm. On the right-hand side, I'm talking about our new proposed algorithm. So the main difference is in our previous algorithm, we obtain data only from, we rely only on data coming from one single site. When it comes to our proposed algorithm, we take information from two sensors in close proximity with connected flows. And that allows us to ignore detecting actual water quality events as anomalies. And another difference is now our previously proposed algorithm is a completely unsupervised algorithm. That means we don't really need any labeled data sets in our proposed algorithm. Now, in our proposed algorithm, it is kind of a semi-supervised algorithm. The reason for me to call it as semi-supervised is now we are going to take information coming from upstream sensor. We are going to use that information to predict downstream sensor. Now, in that case, we assume that our upstream sensor is free from outliers. That's the only thing. That's the main reason for me to claim it as a supervised approach. And other than that, we don't need any labeled data to make our things work. And another thing is when it comes to our feature-based approach, we calculate the anomalous scores based on distance-based measures. When it comes to our proposed new algorithm, we calculate the anomalous scores based on density. And another thing is, another limitation with our previously proposed algorithm is, even though it's unsupervised, we were agnostic about the outlier scoring method. We really didn't have any confirmation, additional confirmation about our detected anomaly. But now in our proposed algorithm, we are using the information coming from a nearby site. So basically that provides an additional confirmation for our outliers, detected anomalies. So it provides an additional guarantee about our detected anomalies. And another thing is, in both algorithms, we use a data-driven anomalous threshold based on extreme value theory. Now, in one of the advantage of this new algorithm is we release certain assumptions that we made in our oddwater approach. So basically, this is an improved version, and it has much more capabilities compared to our previously proposed algorithm. Okay, so with that, I come to my key takeaways. So my first question, I told you I'm going to answer three main questions. So my first question was, what is an anomaly? So in this work, we really focus on technical issues in sensor equipments. That was our main focus. And according to our proposed algorithm, this is how we define an anomaly. We define an anomaly as an observation with unexpectedly low conditioning probability density. Now, you know what do you mean by conditioning? Basically, you take new information from other sources. And then my second question was, why is it important to use various types of conditioning information? Because we had a really big challenge. We want to differentiate real water quality events from technical issues. With the available statistical anomaly detection methods, we cannot do this one. And now the last question is, how are the two approaches, oddwater and our new approach different? Basically, our previous algorithm takes information only from one side, but our new algorithm takes information from two sensors in close proximity with connected flows. And now our new algorithm can capture both high priority anomalies and low priority anomalies. Okay, so that's basically the end of my talk. So you probably have some questions related to from this talk. But now in this talk, what I try to do is I try to give you the intuition behind our proposed algorithm. And now Priyanga will talk about the theoretical foundation of our proposed algorithm. And then after that, we decided to take a common Q&A session, because most of the questions that you have right now will be addressed by Priyanga. And then after that, we can come for a common Q&A session to discuss further improvements regarding this algorithm. Yes, that's it. Thank you very much for listening.